Welcome to this presentation on the OSWatcher Black Box Analyzer. Starting in Release 4.0, OSWatcher has been renamed to OSWatcher Black Box. This was done to eliminate confusion around the name OSWatcher, as several tools within Oracle now share this same name. For example, there is a version of OSWatcher running on Exadata, which is incompatible with the standard version of OSWatcher, which is what is being described here. There are also versions of OSWatcher for VMS, Windows, etc. OSWG has also been renamed to the OSWatcher Black Box Analyzer. All files associated with OSWatcher Black Box, including the OSWatcher Black Box Analyzer, have been packaged into a single tar file, which is available for download from my Oracle support note number 301137.1. Version 5 has added some new changes to OSWatcher Black Box. The utility now provides a network analyzer to analyze netstat files. Data links and network protocols are checked for errors. Version 5 also collects less data, thereby reducing the footprint of OSWatcher Black Box. An added benefit to smaller archives is the less time it takes to analyze the files. The location of the archive directory is now configurable through the use of an environment variable. The environment variable OSWBB_archive_dest can be set to any device or location. One of the goals of OSWatcher Black Box and OSWatcher Black Box Analyzer is to give the user a flexible architecture, written in shell script, so users can see the code that is actually running on their production servers, and to provide a lightweight operating system monitoring and analysis tool. The term black box is used to describe a simple interface to both collect and analyze operating system metrics, making the user experience as easy as possible. OSWatcher Black Box is now capable of analyzing its own data. There are many advantages to making OSWatcher a black box solution. First, the utility analyzes files automatically. This reduces the amount of time it takes to review large amounts of data, therefore reducing the amount it takes to resolve an issue. Second, the amount and size of the logs collected by OSWatcher Black Box can be overwhelming. There are hourly data files associated with each unique utility that OSWatcher Black Box runs. So for example, in 1 day's time there would be 24 VM stat logs, 24 IO stat logs, etc. Multiply this by the number of days in your archive and you can see this is quite a bit of data to analyze. Third, not everyone has the skill to read and analyze information collected by running the underlying Unix utilities. Because some of these utilities are not standardized across Unix platforms, the same utilities with the same column names can mean different things on different operating systems. Unless the user is intimately familiar with their version of the OS, it can take quite some time to review man pages and associate column names with their actual meaning. Fourth, the analyzer analyzes files automatically, in real time, and drives the focus on the most significant performance problems, lowering the priority of less important problems that do not require immediate attention. Finally, the report the analyzer generates is text-based, making it as easy to upload and cut and paste into a service request, and requires no browser or special application to review the report. So what is the OSWatcher Black Box Analyzer? The OSWatcher Black Box Analyzer is a Java program named OSWBBA.jar. This Java utility is packaged along with OSWatcher Black Box scripts into a single tar file, which is downloadable for my Oracle support. Because the analyzer is written in Java, it can run on any Windows or X-Windows platform. OSWatcher Black Box data collected on Unix servers can either be reviewed on that server, or moved over to the server or PC that has a Windows environment. The analyzer provides graphing capability for CPU, memory, and disk metrics. It produces an HTML report called a system profile, with information on what to look for integrated with graphs, and provides a text-based analysis report, which can be uploaded to a service request. There are 3 basic components to the Black Box Analyzer. First, there is the graphing capabilities, where specific operating system metrics can be graphed over time. Second, an overall system profile report with graphs and integrated text on what to look for. And third, an analysis report which highlights the most significant performance problems to the user. In this slide, we can see on the left-hand side, the different files collected by OSWatcher black box that are used by the analyzer. As you can see, only the VMstat, IOstat, top and netstat log files are used by the analyzer at this time. These files are parsed by the analyzer, and on the right-hand side, we can see the output of the analyzer, the output being graphs of specific OS metrics collected, an analysis report, an HTML profile as described on the previous slide. This slide summarizes the reporting capability of the analyzer. The analyzer will produce text-based analysis of the OSWatcher black box log files. Currently only VMstat, IOstat and top log files are analyzed. In future releases, more metrics from more utilities will be included in the analysis. The analysis report produced by the analyzer is broken down into different sections for easy readability. Each section will be discussed in detail in upcoming slides. The analyzer focuses on finding the most significant problems and orders all problems it finds by the ones having the most significant impact on the system. If possible, after identifying specific problems, the analyzer will dig deeper into looking for specific processes which may be causing the problem. This may not be possible in every case, but if process information exists and can be mapped to the occurrence of a specific performance problem, then the analyzer will try and identify this process. After problem identification, the analyzer will attempt to provide recommendations on how to resolve these performance problems. How to install the black box analyzer. Installation is not required as this utility is available as part of the OSWatcher black box. Once the OSWatcher black box is downloaded from My Oracle support and uncompressed, the analyzer executable can be found in the directory where the OSWatcher black box was installed. There are two modes available for running the OSWatcher black box analyzer. First, this utility can be run by using a menu-driven interface. The syntax for running this command is identified in this slide. The second way to run the utility is from the command line. Using this method allows for the analyzer to easily be scripted into some shell script, cron job or other program. The output of the analyzer can be found in the analysis directory where OSWatcher black box was installed. Every analysis has a uniquely identifiable file name in this directory. The analysis file is broken down into 6 sections for easy readability. Section 1 describes the overall status of each major subsystem. Section 2 identifies the most serious operating system performance problems, which is ordered by the impact to the overall system. Section 3 identifies any other findings in addition to the findings from Section 2. The problems in this section are less important than the problems identified in Section 2. Section 4 lists any detailed CPU findings, such as large run queues and high CPU utilization. Section 5 lists all detailed memory findings, such as the system running low on memory or by swapping processors. Section 6 lists detailed disk findings, such as devices with high service times, high % utilization and throughput problems. Section 7 lists network findings, such as data link errors and UDP, TCP and IP protocols. Section 1 provides a quick heads-up status of each major subsystem. Currently statuses exist for CPU, memory, network and I/O subsystems. Status values are as follows. Status of OK means no problems were detected. Status of warning means attention to that subsystem is required. Status of critical means a problem has been identified and immediate attention is required. Status of unknown means that status could not be determined. Some of the reasons for an unknown status can be missing metrics. Unfortunately, not all operating systems contain metrics that are reliable for critical health assessments to be determined. Memory scan rate is an example. Memory scan rate exists on some platforms such as Sun and AIX but is missing on other platforms such as Linux. Another example is HPUX. HPUX does not support extended disk statistics for the IOstat utility. This means IOstat information collected on HPUX platforms is for all practical purposes useless. Another example of these platform-specific issues is AIX does not come shipped with the standard Unix top utility. AIX uses a non-standard top utility, which is not controllable through Unix shell and cannot be captured by OSWatcher black box. This slide depicts the overall subsystem status for the main 4 subsystems. In this example, we see the status of CPU is critical, the status of memory is warning, the status of I/O is OK, and the status of the network is also OK. The following slides will show how to drill down into each of these different subsystems. Section 2 contains information pertaining to system slowdowns. OSWatcher black box contains timestamp interval information in its log files. Because this timestamp information is essentially a heartbeat, timestamps that are delayed from the expected time can indicate when the system is starting to have significant performance problems so serious that OSWatcher black box itself, as well as all other applications, are starting to slow down. The information in this section contains the following columns pertaining to the slowdowns. The snap time column contains the actual timestamped heartbeat time from the OSWatcher black box log files. The variance column indicates how significant the actual timestamp differential is from its predictive value. For example, a variance of 2.0 would indicate a 200% difference in the actual time from the expected time. The seconds column indicates the amount of time, in seconds, between OSWatcher black box heartbeats. The flags column contains bitmap indicators for CPU, memory and I/O. These flags are used by the analyzer to make decisions on the causes of the slowdowns which are identified in this section. Here we can see the output of section 2. Notice the columns snap time, variance, seconds, and flags, along with the cause column, indicating the top 2 most likely causes of the system slowdown. In this example, we can see a slowdown occurring on Friday, May 27th at 10 hours, 36 minutes, and 4 seconds. We can see the variance score of this slowdown being equal to 1.1, indicating that the predicted versus actual slowdown was affected by 10%. The next column, seconds, shows this snapshot taking 34 seconds, as opposed to the expected value of 30 seconds. The expected time value is known, as it is listed at the top of the file. This means the system slowed down by a factor of roughly 10%. The 10% being reflected in the variance score of 1.1. The flags column can be ignored because these flags are used only by the analyzer to make decisions and are displayed here only to give quick validation of what processes are being used by the analyzer to make decisions. The cause column lists the top 2 most likely causes of the slowdown. In this case, we can see a root process consuming high CPU along with a second cause indicating the system is running low on memory. Because the analyzer has identified a particular root process, it digs deeper and tries to identify the unique process causing the slowdown. In this case, the analyzer has found that during the time of this slowdown, the swapper process owned by root is consuming 74.6% of one CPU on the system. The analyzer may or may not be able to identify root cause at the process level. In this case, the analyzer was able to identify the root cause of the slowdown. After identification, the analyzer gives advice on what you are to look for. In this case, it points back to the process identified above. After the advice section, the analyzer lists the most likely reasons for the slowdown. In this case, the analyzer has advised that the system is under stress due to contention for system resources, specifically memory. All slowdowns detected by the analyzer identified in this section are ordered by the most significant impact on the system. The impact causing the greatest slowdown will be listed first, followed by any other slowdowns. Section 3 lists any other findings in addition to those found in Section 2. Section 2 identifies only issues so severe that it has caused the entire system to slow down, so Section 2 data may not list anything if the system did not actually slow down. This section will list any additional findings related to CPU, memory, network, or I/O, which were less severe. In this example, you can see the analyzer has identified critical findings with respect to CPU and memory. Because these findings are listed as critical, the underlying causes of these should be explored. In Section 4, the detailed findings for CPU metrics are listed. This information is only relevant if the analyzer actually knows how many CPUs are on the system. OSWatcher Black Box tries to gather this information on startup. If OSWatcher Black Box cannot identify the number of CPUs, it prompts the user to manually enter this information, and so the analyzer can make correct decisions based on this value. This section reports details about CPU run queue and CPU utilization. CPU utilization is tracked for all root processes and all Oracle background processes, and warns if any of these processes consume large amounts of CPU. In this example we can see, there were 14,413 snapshots contained in the archive. These 14,413 snapshots represents 100% of all snapshots. Of these 14,413 snapshots, only 41 snapshots had run queue values that were considered high. High being defined as greater than 3 times the number of CPUs. These 41 snapshots represent 0.28% of the total number of snapshots. Additionally, we can see there were 6 snapshots that had run queue values greater than 6 times the number of physical CPUs. These 6 snapshots represent 0.04% of the total number of snapshots. The number of times CPU run queue could be considered high as a relatively low number, less than 1% based on the total number of snapshots. The next line contains very useful information, in that it shows the number of times that CPU run queue was high, and remained high, spanning multiple snapshot intervals. It is not uncommon to have times, even on systems with sufficient CPU resources, when CPU run queue can spike high, which normally would not indicate a problem. If however, the run queue remains high over a number of consecutive snapshot intervals, it can indicate a serious problem. In our example, we can see when CPU run queue did spike high but it did not span consecutive snapshot intervals, meaning these spikes were probably more evenly distributed and not centered around a specific time. In this section we are looking at CPU system utilization, meaning the amount of CPU dedicated to running operating system tasks. In our example, we can see 14,413 snapshots representing 100% of all snapshots. In this top section we are looking at total CPU utilization, meaning we are looking for times when CPU utilization of the entire system exceeded 30%, considered high, and 50%, considered very high. In our example there were no times when the entire CPU resources running in system mode was considered high or very high. To save time we have omitted the section on aggregated CPU utilization, but will look at the time where it processes consumed more than 50% of a single CPU. The snap time, OSPID, %CPU value and OS command are listed in this section. The bottom section lists any time any Oracle background process consumed more than 50% of a single CPU. In this section, the detailed findings for memory metrics are listed. The analyzer currently looks at 2 metrics from VMstat, which may not be available on all versions of Unix and Linux. The VMstat process queue lists the number of processes swapped out to disk. Swapping only occurs when the operating system is under extreme stress for memory resources. The other metric and best indicator of when the system is experiencing a memory resources issue is scan rate. Unfortunately, this metric is not available on all versions of Unix and Linux. The metric, free memory, is not used by the analyzer. Calculations for free memory vary by platform and can include buffered and cached memory, so it can be misleading. In this slide, we can see an example of the memory detailed findings. The top section lists any time when the CPU process queue contained a high value for the number of processes swapped to disk. In this case there were no processes being swapped to disk, and therefore no swapping was occurring. The middle section of the report identifies any time memory scan rate was considered high. In our example, there were 3 times when the scan rate was considered high or very high, and more importantly these times occurred back to back, as we can tell from the high spanning multiple snaps column. Below this section, we can see the actual times and values for scan rates, for those 3 snapshots listed previously that had high values. Section 6. lists specific disk findings for those devices considered to be problematic. Some systems now contain hundreds of I/O devices. Although the analyzer looks at all devices, it only reports on those devices considered to be problematic. The analyzer only reports on those devices which are busy more than 50% of the time or have high service times. This lets us focus on those devices which are problematic, ignoring devices which are not important. Storage arrays are especially problematic in that they contain caches, which skew operating system metrics reported by traditional operating system utilities, like SAR, IOStat, and GLANS. The only reliable metric for debugging storage arrays using traditional utilities is throughput. The analyzer will report throughput distribution for devices which are over 50% busy. The analyzer reports the following metrics with respect to disks. Again, the analyzer is focusing only on those devices which it considers problematic, so not all devices may be reported here. Percent busy for only those devices which are more than 50% busy are reported. Service time for those devices reporting a service time greater than 10 milliseconds are reported. Throughput for those devices which are more than 50% busy are reported. In this example, we can see those devices which have a percent busy greater than 50%. The device listed here is 50% busy or more all the time, and therefore should be investigated. Looking at service time in this example, we can see no devices having a service time greater than 10 milliseconds, therefore no devices are reported in this section. In this example, we can see an example of a device that is greater than 50% busy, and see the throughput distribution of the device. This information is useful in particular for storage arrays. Unfortunately, we cannot tell from IOStat if the device listed here is a storage array or conventional disk device. If this device is in fact a storage array, then throughput can be examined. Looking at the throughput distribution versus percent busy can give an indication of whether the device has acceptable performance. Section 7 lists detailed finding about the network. The analyzer looks for input, output, and collision errors on the network interfaces. IP, UDP, and TCP protocols are also analyzed for specific metrics. Those metrics for these protocols which are considered to be common to most network problems are examined. For example, the retransmission rate for the TCP protocol is calculated and a warning issued if this value exceeds 15%. Significant network problems are listed in Section 3 along with probable causes for these issues. In this example, IP errors are reported in Section 3. The analyzer found bad header checksums and fragments were being dropped. It also lists the probable cause of this issue, specifically that the network was corrupting packets or that the device driver queue may not be large enough. The following slides look at what is reported for the network interfaces and protocols. In this example, we can see in Section 7.1, data links which have input, output or collision errors. Although many data links may be listed in NetStat, the only problematic data link was GE0. Also important to note is the time the errors occurred are also reported. We can see input packet errors occurring at 1932-54. Section 7.2 lists the IP protocol findings. The parameters reported here will vary by operating system and will not always be the same as those listed here. We can see problems with the IP protocol occurring at 1724.02. Section 7.3 lists UDP protocol errors. UDP errors are especially important for those customers who are running RAC, as this is the protocol used for RAC. It is important to avoid any dropped packets in UDP. Section 7.4 lists TCP protocol errors. Retransmission is the most important statistic listed here. The analyzer calculates the retransmission rate. In this example, the retransmission rate is borderline high, 14.62%. A rate of 15% should require an investigation. The information provided in the network detailed section is listed for reference. Significant problems detected will be listed in the top of the analysis report in Section 3. If you have any questions, comments or feedback, please email carl.davis@oracle.com.